Hello, everybody out there in Zoom land. We're continuing section 4.3. There it says 4.3, and this is part 2 of our fabulous presentation. Well, we're up to something really cool and awesome and extremely important, which is that the intersection of two subspaces is a subspace. So I'm going to read the theorem, and then I'll try to explain it in English. If V and W are both subspaces of a larger vector space U, then the intersection of V and W, which we write in set language, this way, V intersect W, that intersection is also a subspace of U. So we're talking now about V and W, but the bigger space U is important because we're working in that arena, and we're actually going to inherit a lot of the cool properties from that arena. But anyway, let's move on. So I'm going to go through the proof, but I want to show you just, picture's worth 1,000 words. So let's just look at the picture here. See, it says figure 411. So U is the giant vector space. V, this circle on the on the left, is one subspace. W is a different subspace. And this little football thing in the middle is the intersection V intersect W. It's the intersection V and W. So our goal now is to prove, we know that U is a vector space. We know that V is a vector space because it's a subspace. Subspace means it's a vector space in its own right, which is a subset of U. And W is also a vector space because it's a subspace. Subspace, by definition, is a vector space. And we want to show that this little green football here is where it says V. It looks like two eyes and a nose. Like that looks like the nose. Anyway, I distract myself sometimes. So we're going to show. That's what we want to show. So I'll go through the proof here. It's very simple, very straightforward, I should say, and then we'll look at it in the picture. So V and W, they're both subspaces of U, and because they're both subspaces, we know again, this is something we've established already, that a subspace has to have a zero vector because every vector space has a zero vector. And of course, it shares the subspaces I'm just mentioning. It's not necessary for the proof here, but I don't think, but they share the same zero vector of U, of the giant space U. Anyway, so we know, so the fact that they both contain a zero vector, that means that V intersect W, that means the green little football there is non-empty because the subspace has to be not empty. It can't be empty. Now we want to show, we've established that all we need to show is, there are 10 qualities of a vector space, but we know that when we have a subset, if we can show that subset is non-empty and it's closed under vector addition and scalar multiplication, that's going to be enough to show that subset is indeed a subspace. So let's get right to it. So we want to show that V intersect W is closed under this. So we want to show that this green football is closed under addition. And we want to let's take two random vectors, V1 and V2. And these two vectors live inside that intersection. So there are two little vectors here, V1 and V2. They live inside that intersection. And by the way, V1 and V2 might be the same vector because this intersection might only be one vector. Who knows? But I'm just saying we're calling them V1 and V2. And now V is a subspace and W is a subspace of U. So that we know that V is closed under vector addition and W is closed under vector addition. Well, since V1 and V2 are both part of V, because if they're part of the intersection of V and W, they're obviously part of V. So the sum V1 plus VW, which is what we're looking at now, that sum has to also be in V. And similarly, the sum, because V is a vector space and it's closed. Well, V1 plus V2 also has to be in W, because since V1 is in W and V2 is in W, their sum has to be in W. So wait a second, we basically established here that V1 and V2 are both in the intersection, and the sum of these two vectors are also in the intersection. How do we know they're in the intersection? Well, if they're both in V and they're both in W, then by definition, they're both in the intersection. Well, that means that V intersect W is closed under addition. So, so in other words, if we have two vectors that live inside this green football and I add them up, well, they're both part of V, so their sum is going to be in V. They're both part of W. The sum is going to be in W. That means that's going to land them right inside this green football because they're part of V and also part of W. So that is the argument. And to show scalar multiplication, it's basically the same idea. If we have a vector inside this green football, it's part of V, it's part of W. So when I multiply it by a scalar, it'll still be part of V and also part of W, which means it'll still be in that green football. That, my friends, is the proof of this very important theorem. By the way, this is an interesting remark here. I never even, the union of two subspaces, once we're talking about intersection, how about unions? Again, these are things we know from set theory. Well, turns out the union of two subspaces is not a subspace. And it's really not hard to show that. Not necessarily a subspace, I should say. And it's not difficult to show that. But we'll leave that as an exercise. Now, I want to end off this section with some examples of subspaces, some famous examples of subspaces of some famous vector spaces. So one very famous vector space that we deal with a lot is the plane, the R2 plane. You always call it the XY plane. Now I'm calling it the R2 plane. Same thing. All right. So let's look at this. Let's look at some subspaces of R2. R2 again. That's what we call the XY plane. So this line here. Here's two parallel lines. So A is the line x plus 2y equals 0. So that's this line down here. B is the line x plus 2y equals 1. That's that line up there. So these two lines look very the same, parallel lines. You know what they say? It's a shame because they have so much in common, yet they'll never meet. Parallel lines. And it turns out that one of these actually is a subspace and one of them is not a subspace, which is shocking because when you look at them, they look kind of the same. They're just two lines. Anyways, two parallel lines. So here's what we're going to say. Well, the truth is there's a lot of ways I could show that the top line is not a subspace, because for one reason, it doesn't go to the origin. Now, who cares if it goes to the origin? Well, the origin that's what the 0 vector is 0, 0. So the fact that the top line does not go to the origin automatically disqualifies it from being a subspace. I don't have to really go any further. There's a million ways I could show the top line is not a subspace, but that's just one. Another way I could show the top line is not a subspace is because this point right there is 1, 0, and if I add it to itself, I get 2, 0, which is over here, which is off the line. So there's a lot of ways I could show that that the top line is disqualified from being a subspace. That's easy. Let's look at the bottom line and see if we could show that is a subspace. Also it'll be not too hard. Let's show. So we're looking at the bottom line now. Bottom line. Hey, the bottom line. So if we solve for x, and we want to solve for x and put it in the parametric form. So this line is really the set of numbers -2t, t, because x is equal to -2ty, and so on and so forth. And this is something we learned how to do this back in, I think in chapter 1 even, how to write things in terms of parametric form. Well, any vector, let's say v1, that's going to be -2t1, t1, whatever t1 whatever t1 is going to be. And if I have a different t2, then that's going to give me vector 2, and that's going to be -t2, t2, not t for 2, but t2. By the way, that was a very, very famous song, like over 100 years ago. 2t for 2 and 2 for t. Anyway, let's see what happens when I add these two vectors. So if I add vector 1 plus vector 2, because that's what I want to do. I want to show that if I add these two vectors, it's going to stay on that line. And let's check it out. So vector 1 is -2t1, t1. Vector 2 is -2t2, t2. And when I add them up, so if I add the -2t1 and the -2t2, and I just factor out the -2. I get -2 times T1 plus T2. But T1 plus T2, that's just another scalar. T1 plus T2 is just another scalar. And here I have comma T1 plus T2, which is also just another scalar. We'll call that scalar T3, just give it a name. And so I have -2 T3 comma T3. Well, guess what? That's exactly the type of point that's going to be on this line. That's what's there. If and only if it's in that form. So anything that's in this form is going to be on the line. So, and T3, as again, I'm defining T3 to be the sum of T1 plus T2 because I just wanted to give it a name to make it shorter. Anyway, I've shown that V1, which is some point on the line, and V2, which is another point on the line, when I add them, I get the result also lies on that same line, which means that line is closed under addition. So this line that goes to the origin is closed under addition. And similarly, if I multiply by a scalar, it'll be the same thing. It'll be the same idea. Which, by the way, just geometrically, if I have a vector coming, on a line, if I multiply it by a scalar, it just stretches it in the same direction or shrinks it in the same direction, or it flips it the other, in the not polar opposite, the 180-degree flip, So when I multiply a vector by a scalar, I think you could see geometrically that it stays on the line. So we see that now this would really work. Really, the argument we just did here would work with any line that goes through the origin. Any line in the plane that goes through the origin, I could do the same trick, but the same procedure. So really, what we've shown here is that any line that goes through the origin is a subspace of R2. We also know that R2 itself is a subspace of R2. We also know that the origin, which is the zero vector, is a subspace of R2. So we have three different subspaces. Not three, well, it's three categories. There's the zero vector, there's the entire plane, and there's any line through the origin. Now, of course, there are infinite lines through the origin, but at least that's a certain category. I could categorize it as a straight line through the origin. Well, guess what? Turns out that those are the only subsets. Those are the only subspaces of R2. So there are only three different subspaces of R2, which is, like I said, the single point 0, 0, all points on a line that pass through the origin, or any point on a line that passes through any line that passes through the origin, meaning the points on that line is a vector space, or the entire plane. So these are the only three possibilities. That's pretty awesome and pretty. So to sum it up, we have the single point, which is this guy right there. We have any line that passes through the origin, which is example of that right here, and the entire plane. So these three vector spaces, these are the only three subspaces of R2. And again, this, of course, there are infinite different lines that go through the plane, but I'm just saying this category is one category. Okay, now we're going to look at an example of something which is not a vector space. In fact, it's sitting right here, the unit circle. Suppose I look at all the points on the unit circle. Well, if I look at the unit, let's say, for example, I have the point 0, 1. Well, if I add 0, 1, and here I have the point 1, 0, and I add them up, I get 1, 1, which is outside the circle. By the way, this is the unit circle, just the circle itself. What if I had the circle but all filled in? Meaning this of course is all the points x squared plus y squared equals 1. What if I had x squared plus y squared is less than 1 or less than or equal to 1? Well, I'm going to have the same problem, because if I add this point plus that point, I'm still going to get a point that's outside the circle. So this is just an example of something which is not a vector space. Or more specifically, this is an example of something which is not a subspace of R2. It's not a vector space in its own right, therefore it's not a subspace of R2. And that's really what we're saying over here. As an example, it's not a subspace. Okay. So let's move on. Oh, you see, it says here this remark. Notice that it doesn't have the zero vector. The unit circle doesn't go through the origin, so that disqualifies it immediately. But I'm saying, even if I would say the points less than or equal to 1, so I'm filling in the middle, like I shade this whole thing in blue, even there, it would not be a vector space because it would not be closed under addition or scalar multiplication, or for that matter. Okay, let's look at now. Let's move on to R3. I'm getting ambitious now. Now we're in 3 dimensions, So let's look at a couple of potential subspaces. This is the point x1, comma x2, comma 1. This is all points of that form. So x and y can roam freely, and z is fixed at 1, which looks like it's actually a plane that parallel to the. It's actually a plane that's parallel to the xy plane. So it's an inch above the xy plane. It's parallel to the xy plane. Well, again, we're very sophisticated. We could disqualify A immediately because it doesn't go through the origin, and the zero vector is 0, 0, 0, which is the origin. So W is going to be disqualified immediately. Now let's look at this one here: x, comma x1 plus x3, comma x3. So this is x. The middle is y plus z, and the end is z. So we have x and z. So this is specifically y is equal to x plus z. Really, I mean, if you think about it. So let's look at B. Well, what is this gonna look like? So this, first of all, it's a non-empty set. That's the first thing. It's a non-empty set, and because it contains a zero vector. Because if I have if x is 0 and z is 0, then y is also going to be 0. So it contains a zero vector. It's non-empty. And it contains a zero vector, which needs to contain a zero vector. So it has all those cool things. And let's just show that it's closed under addition. Well, if I take two vectors in this space, v is v1, v3, and the middle is v1 plus v3. U is u1, u3, and the middle is u1 plus u3. Well, if I add these two and do a little, just redistribute and regroup things, you see that the result is going to be of the same form. That I'm going to have x1, which is u1, which is u1 plus v1. Actually, let me highlight that. X1, which is u1 plus v1, and it just makes it a little more easy to see visually. So x1 is u1 plus v1. X3 is v3 plus u3. I forgot what I said. I should have said v1 plus u1. I hope I did. X3, we're calling that v3 plus u3, and the middle winds up being something of the form the x coordinate plus the z coordinate added up. And we're just writing to the reason we're writing x1, we're trying to make it smaller and simpler. It's always a thing in math, sometimes you make the substitution or you create a new variable to make things simpler. Sometimes it makes it more complicated because where did this new variable come from? What's going on? Help. Anyway, but if I multiply by a scalar, I'm gonna have the same thing, because if my first vector v is of the form v1 on the end, v3 on the other end, the sum of v1 plus v3 in the middle, now I multiply everything by a scalar. Well, I'm going to want to, as you see, I'm going to want to get in the same, it's going to stay in the same form. So what does this look like? Funny you should ask. Let's take a quick. Here I am in one of my favorite websites, which is GeoGebra.org. Now, when it comes to two-dimensional graphs, I love Desmos. When it comes to three-dimensional, I love GeoGebra. Anyway, so the line so what we had was really y equals x plus z, because that was what it was. Whatever, we added the x and the z and got the y. And this here is the plan. And also, it's kind of cool. You can make it spin. You can look at it from different angles. You can make it. You should be able to make it spin. Let's see. I hit that. No. Okay. If you're really good at this, which I guess I'm not, you can make it spin. Either way, but notice I'm playing around here. But notice that it's a plane that goes to the origin. That's really what I want to bring out here. It's a plane that's going through the origin. So let's go back to our okay. So there we go. Now, so a plane. So basically, what I'm trying to say, and this, a spoiler alert, but really any plane that goes to the origin is going to wind up being a vector space, and I can make the same, and I'll be able to make the same kind of argument, or a similar kind of argument. So, in fact, this is what's going to wind up being. If you have R3, a single point of just the origin is a vector space, because that's the famous, zero vector. A the entire R3 is a is going to be a vector space, which we've established many times. A plane that goes to the origin will be a vector space, any plane, which is what we just did in the previous, example. And also a line that goes to the origin. So we're talking about a line in 3D space that goes through the origin. That will also be a vector space, and all for the same reasons. And I can show all of them the same way I showed these last two cases. So it all works, and you can understand. So there we go. These are all the subspaces